grounding electrode conductor from the water main in a 200 amp residential service does not necessarily have to be installed within a conduit. The National Electrical Code, or NEC, specifies particular instances where a grounding electrode conductor, also known as a GEC, is required to be run in a raceway. It is essential to understand these specific instances to ensure compliance with electrical codes and maintain safety. According to the NEC, a grounding electrode conductor must be run within a raceway in only two specific scenarios. The first scenario is when the grounding electrode conductor is larger than 4 American wire gauge copper or 2 American wire gauge aluminum. If the conductor exceeds these sizes, it is mandatory to install it inside a conduit or raceway for physical protection. The second scenario mandating a raceway is when the grounding electrode conductor runs parallel to and is within 3 feet of a ferrous metal conduit. The proximity to ferrous metal can induce circulating currents, which can be minimized by enclosing the grounding electrode conductor in a non-ferrous raceway. In all other cases, where the grounding electrode conductor is 4 American wire gauge copper or smaller, or 2 American wire gauge aluminum or smaller, and is not running parallel to and within 3 feet of a ferrous metal conduit, the grounding electrode conductor can be run bare without requiring a conduit. It is important to ensure that the bare conductor is adequately supported and protected from physical damage in accordance with NEC guidelines. The grounding electrode conductor is a critical component of the electrical grounding system, providing a path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. The NEC specifies the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. Table 250.66 in the NEC provides guidelines for sizing the grounding electrode conductor for various service entrance conductor sizes. The grounding electrode conductor connects to the grounding electrode system, which can consist of various elements such as a metal underground water pipe, a ground rod, a ground ring, or a concrete encased electrode, often referred to as a UFA ground. The grounding electrode system provides a low impedance path to earth, ensuring that the electrical system is properly grounded and protected against fault conditions. When installing a grounding electrode conductor, it is crucial to adhere to the NEC guidelines to ensure safety and compliance. The grounding electrode conductor must be securely connected to the grounding electrode using approved methods such as exothermic welding, listed connectors, or other means specified by the NEC. The connections must be accessible for inspection and maintenance. The grounding electrode conductor should be protected from physical damage by routing it in a manner that minimizes exposure to potential hazards. Where the grounding electrode conductor is subject to physical damage, it should be protected by a conduit or other approved means. When a metal water pipe is used as a grounding electrode, it is required to supplement it with an additional grounding electrode, such as a ground rod or ground ring. This supplemental electrode provides redundancy and ensures that the grounding system remains effective even if the metal water pipe is compromised. The supplemental grounding electrode must be bonded to the metal water pipe with a bonding jumper sized in accordance with NEC Table 250.66. The location of the grounding electrode system should be carefully considered to ensure that it is readily accessible for inspection and maintenance. The grounding electrode system should be located as close as practicable to the service entrance equipment. When multiple grounding electrodes are used, they should be spaced at least 6 feet apart to minimize the interaction between their respective zones of influence. The grounding electrode conductor must be continuous from the service equipment to the grounding electrode, without any splices or joints. If a splice is unavoidable, it must be made using reversible compression connectors or exothermic welding. The grounding electrode conductor should be run in a straight line as much as possible, avoiding sharp bends or kinks that could increase impedance. The installation of the grounding electrode conductor should be performed by a qualified electrician who is familiar with the NEC requirements and local electrical codes. The electrician should inspect the grounding electrode conductor and connections to ensure that they are properly installed and meet the NEC standards. Regular inspections of the grounding electrode system should be conducted to verify its effectiveness and identify any potential problems. The grounding electrode resistance should be measured periodically to ensure that it is within acceptable limits. The NEC specifies a maximum grounding electrode resistance of 25 ohms for a single ground rod. If the resistance exceeds 25 ohms, an additional ground rod or other grounding electrode is required. The grounding electrode system is an essential part of the overall electrical safety system, providing a path for fault current to return to the source and helping to protect people and property from electrical hazards. By following the NEC guidelines and best practices for grounding electrode conductor installation, you can ensure that the electrical system is properly grounded and safe. Remember to consult the latest edition of the NEC and local electrical codes for specific requirements in the area. Proper grounding ensures safety and minimizes the risk of electrical shock and fire. Grounding electrode conductors play a key role in this. A grounding electrode conductor connects the service equipment or the separately derived system to a grounding electrode. This electrode is typically a ground rod, a metallic water pipe, or a concrete encased electrode. The main purpose of a grounding electrode conductor is to provide a low impedance path for fault current to return to the source. This, in turn, helps the overcurrent protection devices to operate effectively and clear the fault quickly. NEC Article 250.64 covers the requirements for grounding electrode conductors. This section specifies the acceptable materials, the installation methods, and the protection requirements for grounding electrode conductors. The size of the grounding electrode conductor is determined by NEC Table 250.66, which is based on the size of the service entrance conductors or the derived phase conductors. It's important to select the correct size to ensure adequate fault current carrying capacity. Grounding electrode conductors must be securely connected to the grounding electrode. Acceptable methods include exothermic welding, listed pressure connectors, listed clamps, and other approved means. The connection must be accessible for inspection and testing. While running the grounding electrode conductor, it should be protected from physical damage. If it's exposed to physical damage, it must be installed in rigid metal conduit, intermediate metal conduit, rigid non-metallic conduit, electrical metallic tubing, or cable armor. As previously mentioned, conduit isn't always required. A bare copper conductor can be used if it's not subject to physical damage and meets other requirements. The NEC specifies that the grounding electrode conductor must be continuous. This means that it should not have any splices or joints. If a splice is unavoidable, it must be made using irreversible compression connectors or by exothermic welding. The grounding electrode conductor should be run as straight as possible and be securely fastened in place. Avoid sharp bends and long unsupported runs. The NEC requires that the grounding electrode conductor be connected to a grounding electrode. Common grounding electrodes include metal underground water pipes, ground rods, ground rings, and concrete encased electrodes. If a metal underground water pipe is used as a grounding electrode, it must be supplemented by an additional electrode, such as a ground rod or ground ring. This ensures that the grounding system remains effective even if the water pipe is disconnected or becomes non-conductive. Ground rods must be driven into the ground to a depth of at least 8 feet. If rock bottom is encountered, the ground rod can be buried horizontally in a trench that is at least 30 inches deep. Ground rings must be buried at a depth of at least 30 inches and must encircle the building or structure. Concrete encased electrodes, also known as UFA grounds, must consist of at least 20 feet of bare copper conductor that is encased in concrete. The concrete must be in direct contact with the earth. It is important to note that the requirements for grounding electrode conductors can vary depending on the specific application and the local electrical codes. Always consult the latest edition of the NEC and local codes to ensure compliance. A qualified electrician should perform grounding electrode conductor installations. Grounding is crucial for electrical safety, reducing the risk of electric shock and minimizing the potential for equipment damage. Properly installed grounding electrode conductors play a vital role in achieving these goals. The information provided here is for general guidance only and does not constitute professional electrical advice. Always consult with a qualified electrician for specific installation requirements. Consider a scenario where you're upgrading a residential electrical service from 100 amps to 200 amps. The existing grounding electrode conductor is a 6 American wire-gauge copper conductor connected to a ground rod. According to NEC Table 250.66, a 4 American wire-gauge copper conductor is required for a 200 amp service with copper service entrance conductors. Therefore, the grounding electrode conductor must be upgraded to at least a 4 American wire-gauge copper conductor. In this case, the 4 American wire-gauge copper conductor does not need to be installed in conduit unless it is subject to physical damage or run within 3 feet of a ferrous metal conduit. You decide to drive a second ground rod to supplement the existing ground rod. The 2 ground rods must be spaced at least 6 feet apart. The grounding electrode conductor must be connected to both ground rods using reversible compression connectors or exothermic welding. The resistance to ground of the grounding electrode system should be tested to ensure that it does not exceed 25 ohms. If the resistance exceeds 25 ohms, additional ground rods or other grounding electrodes may be required. In another scenario, consider a commercial building with a 480 volts/277 volts Y-connected electrical system. The grounding electrode conductor is connected to a metal underground water pipe and a ground ring. The metal underground water pipe must be supplemented by the ground ring. The grounding electrode conductor is sized according to NEC Table 250.66, based on the size of the service entrance conductors. Because the grounding electrode conductor is larger than 4 American wire-gauge copper, it must be protected from physical damage by installing it in rigid metal conduit, intermediate metal conduit, or rigid non-metallic conduit. The grounding electrode conductor is connected to the metal underground water pipe using a listed grounding clamp. The grounding electrode conductor is connected to the ground ring using exothermic welding. The ground ring encircles the building and is buried at a depth of at least 30 inches. The resistance to ground of the grounding electrode system is tested to ensure that it meets the requirements of the NEC and local electrical codes. Proper grounding is essential for the safety and reliable operation of electrical systems. Grounding electrode conductors play a crucial role in providing a low impedance path for fault current to return to the source. By following the NEC requirements and best practices, you can ensure that electrical systems are properly grounded and protected from electrical hazards. The specific requirements for grounding electrode conductors can be complex and vary depending on the specific application. Always consult with a qualified electrician and refer to the latest edition of the NEC and local electrical codes for detailed guidance. Grounding electrode systems should be inspected and tested regularly to ensure their effectiveness and identify any potential problems. Regular maintenance and testing can help to prevent electrical hazards and ensure the continued safe operation of electrical systems. Electrical safety is paramount, and proper grounding is a critical component of a safe electrical system. By understanding the requirements for grounding electrode conductors and following best practices, you can help to protect people and property from electrical hazards. Always prioritize safety when working with electrical systems and consult with qualified professionals for assistance. Remember, electrical work should only be performed by qualified and licensed electricians. Never attempt to perform electrical work unless you have the necessary training and experience. Electricity can be dangerous, and improper installation or maintenance can lead to serious injury or death. Always follow safety precautions and use appropriate personal protective equipment when working with electrical systems. Turn off the power before working on any electrical equipment. Use a voltage tester to verify that the power is off before touching any wires or components. Wear safety glasses and insulated gloves to protect yourself from electrical shock and other hazards. Be aware of your surroundings and avoid contact with any conductive surfaces. If you are not comfortable performing electrical work, hire a qualified electrician to do the job. Your safety and the safety of others should always be your top priority. Grounding electrode conductors are a vital part of electrical safety and should be installed and maintained in accordance with the NEC and local electrical codes. Proper grounding can help to prevent electrical shock, reduce the risk of fire, and protect electrical equipment from damage. Always consult with qualified professionals and prioritize safety when working with electrical systems.